Good morning. Let's make some audio training data. We have a lot of audio files here, all these bird sounds, and we need to convert them into something that we can feed into a model. So what we're going to do is we're going to use a fast Fourier transform over that audio data to create a spectrogram that we can turn and feed into a model. Just condenses all of that audio data down into something a lot smaller and a lot easier to go through a model. So what a fast Fourier transform does is it's a Fourier analysis converts a signal from its original domain to representation of another domain. So we're usually, in this case, we're going to frequency to time, or time to frequency. And what we'll be doing here is we'll be going from time over to frequency. So we can look at the different values in each individual frequency to see, in this case, what the amplitude was. We're going to be using a custom function for this fast Fourier transform, so that way we can use the same math in JavaScript that we're using over here in Python. So let's get into it. The few things that we really need are going to be the transform function from Nayuki. You can just find that on, if you Google Nayuki, he has some custom fast Fourier transform mathematics. And he's written them in C and Python and JavaScript, several different languages. And so it's nice to be able to pull it in and you get the exact same results if you pass the wave in JavaScript or if you pass it in Python. You need to make sure you get the same output coming in. You can't just use the SciPy function to create a spectrogram from it because we don't have that same function in JavaScript. And this project, we're moving it over to JavaScript. Anyway, we grab pool from multiprocessing because we're going to do all of this in parallel. We have a lot of files to go through and we want to go through them as quick as possible. Even at that, it takes about 8 hours to run the first part of this function and then about 4 to 6 hours to run the second part. Here's just some data or variables that we're setting. We're using 16K audio. For the FFT, we're setting W to 1024. Our spectrograms coming out are going to be 512 by 512. And we're skipping over each one by 256 units. So if we take a 512 by 512 spectrogram, we're skipping over by 256 to create the next spectrogram. And then our max seconds are 300. So if we have long audio files, we're capping them at 5 minutes. So we're going to be pulling in all of our bird information, which is just our list of birds and then all the audio files for each bird. Then we have these two main functions here, download and wave. That's where we're downloading the MP3 file and then we're converting it to a single channel 16K wave. 16K because that's the same sample rate that we can use in iOS and also on Android with the Web Audio API. And then we're creating the spectrogram from it. So here we have wave data coming in and we are chopping that wave data up into segments that are half of W in size. And then we are using the transform value to transform that audio data into a fast Fourier transform, or fast Fourier data. We're converting it from a time domain into a frequency domain there. And then we're taking the square root of the real value and the imaginary value squared. This just gives us the amplitude coming out. And then we're taking just half of the value coming out because the other half is the mirrored side. So in a spectrogram, if you look at it, you have one side that's the pertinent data that we use. The other side is just almost a mirror of it, and we're going to trash that. We're going to normalize the data coming out, taking the logarithm of the spectrogram, and then taking the mean value of it, then returning the spectrogram. You can see we're going to be doing this for 125,000 different audio files. I know that because, like I said, this has already been ran. We're just going through and seeing how it gets ran, so that way I don't have to try to make a 12-hour video. That'd be disturbing. Okay, so we have this main function here, getBird, and getBird is what's going to be calling those other two functions. We're going to pass into it I, which is just having I has the bird index, the item values, and then some random number. Because each time we call this, it's going to sleep for some random number of 10 seconds. So that way all iterations at the same time aren't being called. I'll show you why that matters here in just a moment. Anyway, we're just making a spectrogram directory, getting the list of audio files here, and then we're looping through all of the assets that we have, all of those different audio files. And we're going to download it and turn it into a wave. We're going to take that wave and convert it into float data here. So we're taking the integer value and dividing it by the max integer value, telling NumPy that it is now a float 32 value. And then we're sending it in to create spectrogram to create the spectrogram from that audio data. Then here is where we're chopping that long spectrogram up into 512 by 512 pieces, skipping over by 256 each time, and saving it just as a CSV value to a .spectro file. It's probably a more efficient way to do that, but that works really well for our use case here. And then, so we have the bird items, and we have these random numbers, and we're creating an array from them. And then we're passing it into our pool right here with pool.map getBird, which is our control function with all the bird items. And then it calls, it calls getBird for each bird item, and it does it 90 at a time. And that takes about 8 hours to run through. You can see right here we have a failed request of a 404. And usually that happens because too many requests are being made at one time, which is why we have each individual item in the pool kind of sleep for a few seconds to help stagnate them to where all of 90 are not running at the exact same time or at the same process in their loops. Okay, so at this point here, we have spectrograms. We have .spectro files for each audio file for each bird. It's a lot of different data. It's like 5 terabytes of data. So this next part here is where we take those spectrograms and we turn them into TFRecords. We use TFRecords because we don't want the hard drive to be the bottleneck in the training process. Originally, I just attached a GPU on the training process and thought like, okay, this is going to go a lot quicker. But then I looked at how much that GPU is being utilized, and it was only being utilized like 7 to 8%, very little. And I was trying to figure out why that was the case. Turns out the hard drive was the bottleneck. So the secret to get around that is to do as much pre-processing of all your training data as possible before you actually call the fit function. And so here we're creating TFRecords, so it serializes all the data. It can just be read out and fed into the model pretty much in real time. And we're also going to shuffle all of that data as well, so we don't have to worry about trying to read in all of the data, shuffle it in batch, and then move it to the model. Again, all of the pre-processing is do as much pre-processing as possible before you actually call the fit function. So this is how we create that TF record, right? We have another control function, make TF records. We have a task index. So in this case, we are just going to be running this 90 times. And then, so we're going to create 90 TF record files, and each one is going to randomly select which indexes are in it for each example, and which spectrograms end up making up that example. So for index here, index and range 50,000. We're just going to be adding 50,000 examples to each TF record file because I found that that number fits best in the amount of hard drive space that I have available. Again, this process here takes about another 4 terabytes. And I had about a 10 terabyte limit on my Google Cloud instance, so that's what we're using. And here we are randomly selecting the class index. So we have in classes of 1002. So we're going to randomly select the class index. We're going to look at all the files that we have available for that class index, and we're going to randomly choose one spectrogram file to use. Then we're going to take that spectrogram file, read it in, and convert all of that CSV value into an actual list. And then whenever it comes to creating TF record, this is the most confusing syntax, where we create a features dictionary. We have a class here. The class is really just an int64 list with one value, and that is our class index. Our spectrogram is another feature of a float list, and that's all the float values for the spectrogram. Then we have the example. We're just wrapping it again here in TF train example, and then we're writing it to our TF record file. And then we loop around and we do it again. Pick a random class, pick a random spectrogram that we have from that class, write it to a TF record. Do that 50,000 times by 90, because we're creating a pool of 90 and mapping that make TF records over a range of 90. So calling it 90 times. And you can see the output here. We're starting and it just loops through, and it creates all 90 files, adding more and more and more examples to them. So next we can actually use all this data to train a model and be confident that the hard drive is not our bottleneck. And so we can get it trained as quick as possible and as efficiently as possible, because using 1,002 classes on your model, it's a big feat. So this is how we do that. Thanks for watching. Stick around for the next video where I think we will be training a model.